Hello. Today's topic of lecture is calculus of several variable part 2, that is homogeneous function and Euler's theorem. I am Mr. S.R. Gaikwad, Department of Mathematics, Arts, Commerce and Science College, Jawal. Please subscribe my YouTube channel Parisram Maths Academy. The first topic is homogeneous function. Definition of homogeneous function. A function e of in bracket x comma y is homogeneous function of degree n if f of x comma y equal to x raised to n into f of y upon x, or f of tx comma ty equal to t raised to n into f of x comma y. If this condition is satisfied, then function e of in bracket x comma y is called homogeneous function of degree n. For example, first you can take the function f of x comma y equal to x cube plus 2x square into y minus y cube. First replace x by tx, y by ty, and therefore equal to t raised to 3 x raised to 3 plus 2t square x square into ty minus t cube y cube. Then from each term we can take t cube as common, in bracket x cube plus 2x square y minus y cube. But this bracket term nothing but given function f of x comma y, and therefore f of tx comma ty equal to t raised to 3 into f of x comma y. Here degree of t is 3, and therefore f in bracket x comma y is homogeneous function of degree 3. Second example, f of x comma y equal to x square plus 2xy upon the root of x minus y bracket test 1 by 5. First replace x by tx, y by ty. Therefore t square x square plus 2 tx into ty upon root of tx minus ty bracket test 1 by 5. Here from the numerator we can take t square as common, from denominator we can take root of t as common, and therefore f of tx comma ty equal to t square upon root of t bracket test 1 by 5 into x square plus 2xy upon root of x minus y bracket test 1 by 5. Here t raised to 2 upon root of t, that is degree of the numerator is 2 and degree of denominator is 1 half, therefore 2 minus 1 half, that is 3 by 2, and therefore this term nothing but t raised to 3 by 2. T raised to 3 by 2 bracket test 1 by 5, it means t raised to 3 by 10 into f of x comma y. It means f of tx comma ty equal to t raised to 3 by 10 into f of x comma y, and therefore f is homogeneous function of degree 3 upon 10. This definition of homogeneous function and examples of homogeneous function. Next, Euler's theorem on homogeneous function. First statement of Euler's theorem. If f in bracket x comma y has continuous first order partial derivatives and is homogeneous function of degree n, then x into dou by f dou by x plus y into dou by f dou by y equal to n into f of x comma y. This statement of the Euler's theorem. Proof. Let f in bracket x comma y has continuous first order partial derivatives and is homogeneous function of degree n. Now f is homogeneous function of degree n, therefore by definition of homogeneous function f of x comma y equal to x raised to n into capital F of y upon x, and therefore derivative of function f with respect to x, it means dou by f dou by x equal to find derivative of right hand side apply product formula. First you can take f of y upon x as constant, derivative of x raised to n is n into x raised to n minus 1 plus x raised to n constant, derivative of f of y upon x is f dash of y upon x into derivative of y upon x, in which y is constant, derivative of 1 upon x is minus 1 upon x square, it means derivative of y upon x is minus y upon x square. And therefore by multiplying x we get x into dou by f dou by x equal to n into x raised to n minus 1 into x, nothing but x raised to n into f of y upon x. Then second term is here minus. If you multiply by x, we get x raised to n minus 1 into y into f dash of y upon x. Here x raised to n upon x square, we get x raised to n minus 2, and multiply by x, we get x raised to n minus 1, and then into y into f dash of y upon x. This derivative of function f with respect to x into x. This is equation number 1. Again differentiating function f with respect to y. To find derivative of function f with respect to y, at that time x raised to n is constant term. Derivative of f of y upon x is f dash of y upon x into derivative of y upon x with respect to y is 1 upon x, because the derivative of y is 1. And then multiply by y, and if y into dA by f dA by y equal to x raised to n upon x, nothing but x raised to n minus 1 into y into f dash of y upon x, equation number 2. Then adding equation number 1 and 2, we get x into dA by f dA by x plus y into dA by f dA by y equal to n into x raised to n into f of y upon x minus x raised to n minus 1 into y into f dash of y upon x. This value of x into dA by f dA by x from equation number 1, plus from equation number 2 y into dA by f dA by y, nothing but x raised to n minus 1 into y into f dash of y upon x. Second and third term cancel, and therefore equal to n into x raised to n into f of y upon x. But n into x raised to n into f of y upon x, nothing but small f of x comma y. And therefore x into dA by f dA by x plus y into dA by f dA by y equal to n into f of x comma y. And therefore if f in bracket x comma y is homogeneous function of degree n, then x into dA by f dA by x plus y into dA by f dA by y equal to n into f of x comma y, which is proof of the Euler's theorem. Next theorem. If f in bracket x comma y be homogeneous function of x and y of degree n, having continuous first and second order partial derivatives, then x square into dA by square f dA by x square plus 2xy into dA by square f dA by x dA by y plus y square into dA by square f dA by y square equal to n into n minus 1 into f of x comma y. One more theorem. If u equal to g inverse of x raised to n into capital F of y upon x, then x into dA by f dA by x plus y into dA by f dA by y equal to n into g of u upon g dash of u, where g of u equal to x raised to n into f of y upon x. Then we can take examples on these three theorems. First example. Verify Euler's theorem for the function f of x comma y equal to x cube plus y cube minus 3x square into y. Solution. Let f of x comma y equal to x cube plus y cube minus 3x square into y. Here degree of x is 3, degree of y is 3. Here degree of x is 2, degree of y is 1. Therefore degree of third term is also 3. It means degree of each term is 3. And therefore f in bracket x comma y is homogeneous function of degree 3. And therefore by Euler's theorem, x into dA by f dA by x plus y into dA by f dA by y equal to 3 into f of x comma y. Now to verify the Euler's theorem, it means we can find the value of dA by f dA by x, multiply by x, and value of dA by f dA by y, multiply by y, and taking their addition, and we have to check equal to 3 into f of x comma y or not. Verification. Let derivative of function f with respect to x. It means dA by f dA by x equal to derivative of x cube is 3x square, derivative of y cube is 0, minus derivative of 3x square y is minus 6xy, because the derivative of x square is 2x. It means derivative of f nothing but 3x square minus 6xy. Derivative of function f with respect to y equal to derivative of first term is 0, derivative of y cube is 3y square minus derivative of 3x square y with respect to y is 3x square, because the derivative of y is 1. Multiply dA by f dA by x by x, multiply dA by f dA by y, we get x into dA by f dA by x equal to 3x cube minus 6x square y, and y into dA by f dA by y equal to 3y cube minus 3x square into y, and then by taking their addition. And therefore x into dA by f dA by x plus y into dA by f dA by y equal to 3x cube minus 6x square y plus 3y cube minus 3x square y. and therefore equal to 3x cube plus 3y cube minus 6 minus 3, that is minus 9x square y. Then from this right hand side we can take 3 as common, in bracket x cube plus y cube minus 3x square y. But this x cube plus y cube minus 3x square y nothing but given function f of x comma y. And therefore x into dA by f dA by x plus y into dA by f dA by y equal to 3 into f of x comma y. And therefore from equation number 2 and 3 Euler's theorem is verified. Next example. If u equal to tan inverse of x cube plus y cube upon x plus y, then prove that number 1, x into dA by u of dA by x plus y into dA by u of dA by y equal to sine of twice u. And second, x square into dA by square u of dA by x square plus 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to sine of twice u into 1 minus 4 sine square u. Solution. Let u equal to tan inverse of x cube plus y cube upon x plus y. First you can transfer this tan inverse in left hand side. We get tan of u equal to x cube plus y cube upon x plus y. And therefore we can take tan of u equal to f of x comma y, where f of x comma y equal to x cube plus y cube upon x plus y. Here degree of the numerator is 3 and degree of denominator is 1. 3 minus 1, that is 2. It means f in bracket x comma y is homogeneous function of degree 2. And therefore by Euler's theorem x into dA by f dA by x plus y into dA by f dA by y equal to 2 into f of x comma y. It means x into dA by f dA by x plus y into dA by f dA by y equal to 2 into f of x comma y nothing but tan of u. Now f of x comma y equal to tan of u. Derivative of function f with respect to x, it means dA by f dA by x equal to derivative of tan of u is sec square u into derivative of u nothing but dA by u of dA by x. And dA by f dA by y equal to derivative of tan of u is sec square u into dA by u of dA by y. Then we can substitute the value of dA by f dA by x and dA by f dA by y in this equation. And therefore we get x into value of dA by f dA by x is sec square u into dA by u of dA by x plus y into value of dA by f dA by y is sec square u into dA by u of dA by y equal to 2 into tan of u. Then by dividing sec square u we get x into dA by u of dA by x plus y into dA by u of dA by y equal to 2 into tan of u upon sec square u equal to 2 into, but tan of u is same as sin u upon cos u into value of 1 upon sec square is same as cos square u. Then cos of u cancel equal to 2 times sin of u into cos of u. But 2 times sin u into cos of u nothing but sin of twice u. This is proof of the first part. Then second part. To prove the second part, first you can differentiate equation 1 with respect to x partially. We get to find derivative of x into dA by u of dA by x with respect to x, we can apply the product formula. First you can take x constant. Derivative of dA by u of dA by x with respect to x is dA by square u of dA by x square plus dA by u of dA by x constant into derivative of x is 1. Plus to find derivative of second term with respect to x, at that time y is constant. Derivative of dA by u of dA by y with respect to x is dA by square u of dA by x dA by y equal to derivative of sin of twice u is cos of twice u into derivative of twice u is 2. Therefore 2 into cos of twice u into derivative of u is dA by u of dA by x. Then we can transfer the second term in right hand side. We get right hand side is 2 into cos of twice u into dA by u of dA by x minus dA by u of dA by x. Then from right hand side we can take dA by u of dA by x as common. We get 2 into cos of twice u minus 1 into dA by u of dA by x. Then multiply by x on both sides. We get x square into dA by square u of dA by x square plus xy into dA by square u of dA by x dA by y equal to 2 into cos of twice u minus 1 into x into dA by u of dA by x, which is equation 2. Then again we can differentiate equation 1 with respect to y partially. To find derivative of equation 1 with respect to y, at that time we can apply the product formula for a second term. In first term x is constant, and therefore differentiate equation 1 with respect to y partially, we get first x constant, derivative of dA by u of dA by x with respect to y is dA by square u of dA by y dA by x, plus in second term we can apply product formula y constant, derivative of dA by u of dA by y with respect to y is dA by square u of dA by y square, plus dA by u of dA by y constant into derivative of y is 1 equal to right hand side derivative of sine of twice u is 2 times cos of twice u into derivative of u with respect to y is dA by u of dA by y. Then this third term, this dA by u of dA by we can transfer in right hand side. We have 2 into cos of twice u into dA by u of dA by y minus dA by u of dA by y. Then from right hand side we can take dA by u of dA by y as common. We have 2 into cos of twice u minus 1 into dA by u of dA by y, and then multiply by y on both sides. We get xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to 2 into cos of twice u minus 1 into y into dA by u of dA by y. Equation number 3. Then adding equation number 2 and 3, we get the first term of left hand side of equation number 2 is x square into dA by square of dA by x square. Second term of equation number 2 and first term of equation number 3 both are same, and therefore 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to the right hand side of equation number 2 is 2 into cos of twice u minus 1 into x into dA by u of dA by x plus from equation number 3 right hand side is 2 into cos of twice u minus 1 into y into dA by u of dA by y. Then from right hand side we can take bracket term as common. We get 2 into cos of twice u minus 1 into in bracket x into dA by u of dA by x plus y into dA by u of dA by y. But value of this bracket term from equation number 1 nothing but sine of twice u, and therefore 2 into, by using trigonometric formula, value of cos of twice u is 1 minus 2 times sine square u, then minus 1 into sine of twice u, and therefore equal to sine of twice u into 2 minus 4 sine square u minus 1, and therefore x square into dA by square u of dA by x square plus 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to sine of twice u into 2 minus 1, that is 1 minus 4 sine square u, which is a required solution of the given example. Next example, if u equal to sine inverse of x raised to 1 by 4 plus y raised to 1 by 4 upon x raised to 1 by 6 plus y raised to 1 by 6, then prove that first x into dA by u of dA by x plus y into dA by u of dA by y equal to 1 upon 12 into tan of u, and second x square into dA by square u of dA by x square plus 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to 1 upon 144 into tan of u into tan square u minus 11. Solution. Let u equal to sine inverse of x raised to 1 by 4 plus y raised to 1 by 4 upon x raised to 1 by 6 plus y raised to 1 by 6, and therefore we get sine of u equal to x raised to 1 by 4 plus y raised to 1 by 4 upon x raised to 1 by 6 plus y raised to 1 by 6. We can transfer this sine inverse in left hand side, we get sine u, and therefore we can take sine of u equal to f of x comma y, where f of x comma y nothing but x raised to 1 by 4 plus y raised to 1 by 4 upon x raised to 1 by 6 plus y raised to 1 by 6. Here degree of the numerator is 1 upon 4, degree of denominator is 1 upon 6, and therefore 1 by 4 minus 1 by 6, LCM is 12. Numerator is 3 minus 2. And therefore 3 minus 2 upon 12 and we equal to 1 upon 12. It means f in bracket x comma y is homogeneous function of degree 1 upon 12. And therefore by Euler's theorem, x into dA by u of dA by x plus y into dA by u of f x into dA by f by dA by x plus y into dA by f by dA by y equal to 1 upon 12 into f of x comma y. But here f of x comma y nothing but sine of u. Now f of x comma y equal to sine u, derivative of f with respect to x nothing but derivative of sine of u is cos of u into dA by u of dA by x, and dA by f by dA by y equal to cos of u into dA by u of dA by y. This derivative of function f with respect to x and with respect to y. Then we can substitute the value of dA by f by dA by x and dA by f by dA by y in above equation. We get x into value of dA by f by dA by x is cos of u into dA by u of dA by x plus y into value of dA by f by dA by y is cos of u into dA by u of dA by y equal to 1 upon 12 into sine of u. Then by dividing cos of u, and therefore x into dA by u of dA by x plus y into dA by u of dA by y equal to 1 upon 12 into sine u upon cos of u, that is tan of u. This solution of the part first. Then to find solution of part second, first differentiate equation 1 with respect to x partially. We get to find derivative of first term, again apply here product formula. First term constant, derivative of second term is dA by square u of dA by x square plus dA by u of dA by x constant, derivative of x is 1, plus to find derivative of second term at that time y is constant, derivative of dA by u of dA by y with respect to x is dA by square u of dA by x dA by y equal to right hand side 1 upon 12 into derivative of tan of u is sec square u into dA by u of dA by x. Again here this dA by u of dA by x, this second we can transfer in right hand side. We get 1 upon 12 into sec square u into dA by u of dA by x minus dA by u of dA by x. Then from right hand side we can take dA by u of dA by x as common. We get 1 upon 12 into sec square u minus 1 into dA by u of dA by x. Then multiply both side by x. We get x square into dA by square u of dA by x square plus xy into dA by square u of dA by x dA by y equal to 1 upon 12 into sec square u minus 1 into x into dA by u of dA by x, equation number 2. Again differentiate equation 1 with respect to y partially. We get in first term x into derivative of dA by u of dA by x with respect to y is dA by square u of dA by y dA by x, plus in second term by applying product formula, first y constant, derivative of dA by u of dA by y with respect to y is dA by square u of dA by y square plus dA by u of dA by y constant into derivative of y is 1 equal to right hand side 1 upon 12 into derivative of tan of u is sec square u into dA by u of dA by y. We can transfer this last term, third term in right hand side. We get 1 upon 12 into sec square u into dA by u of dA by y minus dA by u of dA by y. Then in right hand side we can take dA by u of dA by y as common. We get 1 upon 12 into sec square u minus 1 bracket complete into dA by u of dA by y. Then multiply by y on both sides. We get xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to 1 upon 12 sec square u minus 1 bracket complete into y into dA by u of dA by y. Equation number 3. Then adding equation number 2 and 3, we get the first term of equation 2 of left hand side is x square into dA by square u of dA by x square plus second term of equation number 2 and first term of equation number 3 are same, and therefore 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to right hand side of equation number 2 is 1 upon 12 sec square u minus 1 into x into dA by u of dA by x plus from equation number 3 1 upon 12 into sec square u minus 1 into y into dA by u of dA by y. Then from right hand side we can take 1 upon 12 x square u minus 1 as common. In second bracket, x into dA by u of dA by x plus y into dA by u of dA by y. But value of this bracket term from equation number 1 nothing but 1 upon 12 into tan of u. And therefore 1 upon 12 into this 1 upon 12, that is 1 upon 144 into tan of u into, using trigonometric formula, value of sec square u is 1 plus tan square u minus 12, and therefore equal to 1 upon 144 into tan of u into tan square u plus 1 and minus 12, that is minus 11. And therefore x square into dA by square u of dA by x square plus 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to 1 upon 144 into tan of u into tan square u minus 11, which is solution of the given example. Okay, next we can take next function. If u equal to sine inverse of x square plus y square bracket test 1 upon 5, then prove that x into dA by u of dA by x plus y into dA by u of dA by y equal to 2 upon 5 into tan u. And second, x square into dA by square u of dA by x square plus 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to 2 upon 25 into tan of u into 2 tan square u minus 3. Solution. First, the given function is u equal to sine inverse of x square plus y square bracket is 1 upon 5. It means sine of u equal to x square plus y square bracket is 1 upon 5. Therefore, we can take sine of u equal to f of x comma y, where f of x comma y equal to x square plus y square bracket is 1 by 5. Now, here x square plus y square bracket is 1 upon 5. Degree of each term of bracket term is 2. 2 raised to 1 by 5. It means f is homogeneous function of degree 2 by 5. And therefore by Euler's theorem, x into dA by f by dA by x plus y into dA by f by dA by y equal to 2 upon 5 into f of x comma y, where f of x comma y is sine of u. And therefore, now here f of x comma y nothing but sine of u. Therefore dA by f by dA by x equal to cos of u into dA by u of dA by x, and dA by f by dA by y equal to cos of u into dA by u of dA by y. These are derivative of function f with respect to x and derivative of function f with respect to y. Then we can substitute the value of dA by f by dA by x and dA by f by dA by y in this equation. We get x into value of dA by f by dA by x is cos of u into dA by u of dA by x plus y into cos of u into dA by u of dA by y equal to 2 by 5 into sin u. Dividing by cos of u, we get x into dA by u of dA by x plus y into dA by u of dA by y equal to 2 upon 5 into sin u upon cos u, that is tan of u. This is solution of first part. Then second part. To find solution of second part, first differentiate equation 1 with respect to y partially. We get first term x into derivative of dA by u of dA by x is dA by square u of dA by x square plus dA by u of dA by x constant, derivative of x is 1, plus in second term y constant, derivative of dA by u of dA by y with respect to x is dA by square u of dA by x dA by y equal to 2 by 5 into derivative of tan of u is sec square u into dA by u of dA by x. Then the second term can transfer in right hand side. We get minus dA by u of dA by x. Then from right hand side we can take dA by u of dA by x as common. We get 2 by 5 into sec square u minus 1 into dA by u of dA by x. Multiply both sides by x. We get x square into dA by square u of dA by x square plus xy into dA by square u of dA by x dA by y equal to 2 upon 5 sec square u minus 1 bracket complete into x into dA by u of dA by x. Equation number 2. Then differentiate equation 1 with respect to y partially. We get a first term x constant, derivative of first term with respect to y is dA by square u of dA by y dA by x, plus in second term apply product formula, first y constant, derivative of dA by u of dA by y is dA by square u of dA by y square plus dA by u of dA by y constant into derivative of y is 1 equal to right hand side 2 by 5 into derivative of tan of u is sec square u into dA by u of dA by x. Then this third term is dA by u of dA by x. You can transfer in right hand side. We get minus dA by u of dA by x. Then from right hand side, you can take dA by u of dA by y as common. We get 2 by 5 sec square u minus 1 into dA by u of dA by y. Then multiply by y on both sides. We get xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to 2 by 5 into sec square u minus 1 into y into dA by u of dA by y, which is equation 3. Then adding equation number 2 and 3, we get the first term of equation number 2 is x square into dA by square u of dA by x square plus second term of equation 2 and first term of equation number 3, we get 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to, from equation number 2, the right hand side is 2 by 5 sec square u minus 1 into x into dA by u of dA by x plus from equation 3, 2 by 5 into sec square u minus 1 into y into dA by u of dA by y. Then from right hand side, we can take this bracket term as common. We get 2 by 5 sec square u minus 1 into in bracket x into dA by u of dA by x plus y into dA by u of dA by y. But from the equation number 1, value of this bracket term is 2 by 5 into tan of u. Now we can simplify this first bracket term. From the first bracket term, we can take 1 by 5 as common. We get 2 into sec square u minus 5. Now, therefore 1 by 5 into 2 by 5, that is 2 upon 25 into tan of u into value of sec square u is 1 plus tan square u, and therefore 2 into sec square u nothing but 2 into 2 tan square u minus 5, and therefore equal to 2 by 5 into tan of u into 2 tan square u plus 2 and minus 5, that is minus 3, that is 2 by 25 into tan of u into 2 tan square u minus 3 is solution of the given equation. Okay. Next example. If u equal to log of x cube plus y cube minus x square y minus xy square, then prove that x into dA by u of dA by x plus y into dA by u of dA by y equal to 3. Second, x square into dA by square u of dA by x square plus 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to minus 3. Solution. Let u equal to log of x cube plus y cube minus x square y minus xy square. And therefore we can simplify. If we transfer log in left hand, we cancel this log on right hand side, we get e raised to u equal to x cube plus y cube minus x square y minus xy square. And therefore we can take here e raised to u equal to f of x comma y, where f of x comma y nothing but x cube plus y cube minus x square y minus xy square. Observe that degree of each term in right hand side is 3. And therefore e of in bracket x comma y is homogeneous function of degree 3. And therefore by Euler's theorem, x into dA by f for dA by x plus y into dA by f for dA by y equal to 3 into f of x comma y. But here f of x comma y nothing but e raised to u. Now here f of x comma y equal to e raised to u, and therefore derivative of f with respect to x means dA by f for dA by x equal to e raised to u into derivative of u with respect to x is dA by u by dA by x, and dA by f for dA by y equal to e raised to u into dA by u of dA by y. Then substitute the value of dA by f for dA by x and dA by f for dA by y in this equation. We get x into e raised to u into dA by u of dA by x plus y into e raised to u into dA by u of dA by y equal to 3 into e raised to u. And then by dividing e raised to u, we get x into dA by u of dA by x plus y into dA by u of dA by y equal to 3, which is solution of the first part. Then for second part, similarly differentiate equation 1 with respect to x partially, we get. To find derivative of first term, apply product from, we get x into dA by square u of dA by x square plus dA by u of dA by x into 1 plus in second term y is constant term, derivative of dA by u of dA by y is dA by square u of dA by y x dA by y equal to, in right hand side derivative of constant term is 0. Then second term dA by u of dA by x into 1, we can transfer this second term in right hand side, we get 0 minus dA by u of dA by x, that is equal to minus dA by u of dA by x. then multiply by x, we get x square into dA bar square u of dA by x square plus xy into dA bar square u of dA by x dA by y equal to minus x into dA by u of dA by x, equation number 2. Then differentiate equation 1 with respect to y partially. We get first term x constant derivative of dA by u of dA by x with respect to y is dA bar square u of dA by y dA by x, plus in second term apply the product formula y constant derivative of dA by u of dA by y is dA bar square u of dA by y square plus dA by u of dA by y constant derivative of y is 1 equal to derivative of right hand side is 0. Again this dA by u of dA by y into 1, it means dA by u of dA by y transfer in right hand side, we get 0 minus dA by u of dA by y, that equal to minus dA by u of dA by y, then multiply by y on both sides, get xy into dA bar square u of dA by x dA by y plus y square into dA bar square u of dA by y square equal to minus y into dA by u of dA by y, equation 3. Then adding equation number 2 and 3, we get x square into dA bar square u of dA by x square plus 2xy into dA bar square u of dA by x dA by y plus y square into dA bar square u of dA by y square equal to, from equation number 2 right hand side is minus x into dA by u of dA by x, and from equation 3 minus y into dA by u of dA by y. Taking minus sign as common, therefore x into dA by u of dA by x plus y into dA by u of dA by y. But the value of this bracket term from equation number 1 is 3, and therefore the solution of given answer is x square into dA bar square u of dA by x square plus 2xy into dA bar square u of dA by x dA by y plus y square into dA bar square u of dA by y square equal to minus 3, which is the required answer of the given example. Okay. Next, if u equal to x into phi of y upon x plus psi into y upon x, prove that x square into dA bar square u of dA by x square plus 2xy into dA bar square u of dA by x dA by y plus y square into dA bar square u of dA by y square equal to 0. Solution is given function u equal to x into phi of y upon x plus psi of y upon x. We can take equal to f of x comma y plus g of x comma y, where f of x comma y equal to x into phi of y upon x and g of x comma y equal to psi of y upon x. Clearly here, if you replace x by tx, y by ty, here ta y upon tx, tt cancel, remains only here tx. Tx means degree power of t is 1, and therefore f is homogeneous function of degree 1. If you replace x by tx, y by ty, here tt cancel, here there is no term of degree term of t, it means power of t is 0, it means g is homogeneous function of degree 0, and therefore f in bracket x comma y is homogeneous function of degree 1 and g in bracket x comma y is homogeneous function of degree 0, and therefore by Euler's theorem x into dA by f by dA by x plus y into dA by f by dA by y equal to 1 into f of x comma y, and x into dA by g of dA by x plus y into dA by g of dA by y equal to 0 into g of x comma y, and therefore x into dA by f by dA by x plus y into dA by f by dA by y equal to simply f of x comma y, and second term is x into dA by g of dA by x plus y into dA by g of dA by y equal to 0. Now u equal to f plus g, that is f of x comma y plus g of x comma y. Differentiate derivative of u with respect to x, it means dA by u of dA by x equal to dA by f by dA by x plus dA by g of dA by x. dA by u of dA by y equal to dA by f by dA by y plus dA by g of dA by y, using the rules of differentiation. Also dA by square u of dA by x square equal to dA by square f by dA by x square plus dA by square g of dA by x square, and dA by square u of dA by y square equal to dA by square f by dA by y square plus dA by square g of dA by y square, and dA by square u of dA by x dA by y equal to dA by square f by dA by x dA by y plus dA by square g of dA by x dA by y. These are derivative of u with respect to x, with respect to y, second order derivative and mixed derivative, and therefore but we get x square into dA by square u of dA by x square plus 2xy into dA by square u of dA by x dA by y plus y square into dA by square u of dA by y square equal to value of x square into dA bar square u of dA by x square, we get x square into dA bar square f by dA by x square plus x square into dA bar square g of dA by x square plus value of 2xy into dA bar square u of dA by x dA by y, nothing but 2xy into dA bar square f by dA by x dA by y plus 2xy into dA bar square g of dA by x dA by y. Similarly, value of last term is y square into dA bar square f by dA by x square, y square plus y square into dA bar square g of dA by y square. Then this term we can take the terms of function f only. We get x square into dA bar square f by dA by x square plus 2xy into dA bar square f by dA by x dA by y plus y square into dA bar square f by dA by y square. Similarly, terms of g. Now, we know that if f in bracket x comma y is homogeneous function of degree n, then x square into dA bar square f by dA by x square plus 2xy into dA bar square f by dA by x dA by y plus y square into dA bar square f by dA by y square equal to n into n minus 1 into f of x comma y. If f is homogeneous function of degree n, at that time value of this term is n into n minus 1 into f of x comma y. Here the function f, here function f is homogeneous function of degree 1 and g is homogeneous function of degree 0, and therefore we get here 1 into 1 minus 1 into f of x comma y, because f is homogeneous function of degree 1 and g is homogeneous function of degree 0, and therefore value of this next three term is 0 into 0 minus 1 into g of x comma y. Here 1 minus 1 0, here 0 into g of x comma y, that is second term is also 0, and therefore total right hand side is 0, and therefore x square into dA bar square u of dA by x square plus 2xy into dA bar square u of dA by x dA by y plus y square into dA bar square u of dA by y square equal to 0, which is solution of the given example. Okay, last example. If u equal to sine inverse of x raised to 1 by 3 plus y raised to 1 by 3 upon x raised to 1 half plus y raised to 1 half bracket raised to 1 half, then show that x into dA by u of dA by x plus y into dA by u of dA by y equal to minus 1 upon 12 into tan of u. First given function u equal to sine inverse of x raised to 1 by 3 plus y raised to 1 by 3 upon x raised to 1 half plus y raised to 1 half bracket raised to 1 half, and therefore sine of u equal to this term. Now here we can take g of u equal to, so we can take sine of u as g of u, and therefore g of u equal to x raised to 1 by 3 plus y raised to 1 by 3 upon x raised to 1 half plus y raised to 1 half whole bracket raised to 1 half, where g of u nothing but sine of u. Now here x raised to 1 by 3, degree of the numerator is 1 by 3, degree of the denominator is 1 half, and therefore 1 by 3 minus 1 by 2 by cross multiplication 2 minus 3 upon LCM is 6, that is minus 1 upon 6. Therefore a degree of this inside the bracket term is minus 1 upon 6, minus 1 upon 6 bracket test 1 upon 2. Therefore minus 1 by 6 into 1 by 2, it means this function is homogeneous function of degree minus 1 upon 12, and therefore we know that if u equal to g inverse of x raised to n into f of y upon x, then x into dA by u of dA by x plus y into dA by u of dA by y equal to n into g of u upon g dash of u, and therefore here x into dA by u of dA by x plus y into dA by u of dA by y equal to, here degree nothing but minus 1 upon 12 into g of u nothing but sine of u upon g dash of u, it means derivative of sine of u is cos of u, that is minus 1 upon 12 into sine u upon cos u, that is minus 1 upon 12 into tan of u, and therefore x into dA by u of dA by x plus y into dA by u of dA by y equal to minus 1 upon 12 into tan of u, which is solution of the given example. These are examples of Euler's theorem. First, then summary. To study this topic, first you can remember definition of homogeneous function. How to check the function is homogeneous or not, and what is the degree of the function. At that time we can check the degree of the function. If f of x comma y equal to x raised to n into a capital F of y upon x, or f of tx comma ty equal to t raised to n into f of x comma y, if this condition is satisfied, then function is homogeneous function of degree n. This definition of the homogeneous function. Next, Statement of Euler's theorem. If f is homogeneous function, f has continuous first order partial derivatives and f is homogeneous function of degree n, then x into dA by f for dA by x plus y into dA by f for dA by y equal to n into f of x comma y. This definition statement of the homogeneous Euler's theorem. Now, there is one more theorem. If f in bracket x comma y be homogeneous function of x comma y, x and y of degree n and having continuous first and second order partial derivatives, then at that time x square into dA by square f for dA by x square plus 2xy into dA by square f for dA by x dA by y plus y square into dA by square f for dA by y square equal to n into n minus 1 into f of x comma y. If f is homogeneous function of degree n, at that time this value of this statement. And one more, if u equal to g inverse of x raised to n into capital F of y upon x, then x into dA by u of dA by x plus y into dA by u of dA by y equal to n into g of u upon g dash of u, where g of u nothing but x raised to n into capital F of y upon x. And therefore, if we study this topic, first you can remember all these things, then we get topic is easily. And that, thank you. Please like and share this video, and please subscribe my YouTube channel Parishram Maths Academy.